A healthy human heart beats roughly 100,000 times a day, but the muscle cells driving this action don't actually need a signal from your brain to do it. In fact, if you isolate cardiac cells in a petri dish, they will spontaneously pulse all by themselves. That cellular independence introduces a massive biological danger. If billions of these individual cells fire at their own pace, the tissue simply ripples chaotically. This uncoordinated quivering state, called fibrillation, moves absolutely zero blood. You might assume the solution is for every muscle cell to contract at the exact same moment. But if the bottom chambers squeeze at the identical time as the top chambers, the blood gets trapped in the middle. It physically cannot move between them. The heart is a fluid dynamics engine. To overcome these failure states and push blood effectively, it requires a perfectly timed top-to-bottom sequenced cascade. That cascading rhythm begins in the upper right chamber, inside a specialized cluster of tissue known as the sinoatrial node. This acts as the master pacemaker for the entire organ. The SA node holds this role because its cells possess slightly leaky sodium channels. Positively charged sodium particles constantly bleed through the cell membrane, causing the internal charge to slowly rise until it hits a threshold. This triggers a sudden electrical flash before any other tissue in the heart can fire. The moment that spark generates, it ripples outward, racing instantly across the muscular walls of both upper chambers. This lightning-fast spread is possible because cardiac cells are stitched together by intercalated discs. These tiny structural connections contain tunnels that allow the electrical current to jump directly from one cell to the next without losing speed. Because they communicate instantly, the upper chambers are forced into a unified, simultaneous contraction. They squeeze together, pushing their payload of blood downward. If that electrical wave kept traveling freely downward, the entire heart would contract at once. To prevent that fatal error, a non-conductive barrier of fibrous tissue separates the top and bottom chambers. It physically stops the electrical wave, forcing it toward a single central gateway. That singular gateway is the atrioventricular, or AV, node. The physical structure of the AV node intentionally bottlenecks the electrical current. The signal bogs down as it passes through the narrow cells, creating a mandatory delay of roughly 100 milliseconds. That fraction of a second is a mechanical necessity. It holds off the contraction of the lower ventricles just long enough for them to finish completely filling with the blood pushed down from the upper chambers. The moment the delay is over, the signal bursts out of the bottleneck. It races straight down the center of the heart, through the bundle of His, and curls up the outer walls of the ventricles through a web of Purkinje fibers. Because the electrical signal is delivered to the base of the ventricles first, they contract from the bottom up. Much like squeezing a tube of toothpaste from the bottom, this upward contraction blasts the trapped blood up and out into the body's major arteries. When you look at a standard electrocardiogram, you're watching a direct map of this exact sequence. That small first bump, the P wave, is the electrical signature of the top chambers firing and contracting. The brief flat line that follows is that critical 100 millisecond delay at the AV node, and the large, sharp spike, the QRS complex, maps the massive electrical discharge racing through the lower ventricles to trigger the powerful bottom-up squeeze. A heartbeat is a highly orchestrated electrical chain reaction. The familiar hospital monitor simply traces the physical path of that invisible current. The heart's internal wiring ensures a perfect contraction sequence, but an isolated system has a fatal flaw. A rigid, unchanging rhythm cannot support a human through varying physical demands, like running a marathon or falling into a deep sleep. To manage those changing demands, the nervous system maintains an override. Specialized cardiovascular centers in the brainstem continuously monitor the body's real-time oxygen and pressure needs. Acting as a remote control, the autonomic nervous system sends signals down specific nerve pathways, dropping chemical messengers directly onto the SA node. These chemicals alter the behavior of the sodium channels, either speeding up or slowing down the heart's baseline pace. Modern medicine tracks the success of these rhythmic adaptations using continuous wearable devices. By monitoring the heart over 24 hours, clinicians verify that the spark, the delays, and the brain's real-time adjustments function correctly under daily stress. The human heart sets its own pace and sequences its own contractions with flawless internal logic. It operates with complete mechanical independence, yet remains perfectly synchronized to the ever-changing demands of human life.